So till now we have discussed TTT diagram and CCT diagram. We have also discussed the TTT diagram for eutectoid and hyper-eutectoid and hypo-eutectoid still, and we just have said that for hyper-eutectoid it doesn't change much from the eutectoid still, because the volume fraction of the Fe3C or cemented, which helps in nucleation, is very minimum. Anyway, so now we will be discussing about the different morphologies of the phases. So let us let me draw this thing again clearly. So now we will be discussing about the phase morphology. So for discussing this, let us consider, let us draw the whole TTT curve again. So this is one line, this is another line, this is the other line, and this is one line. So we are considering, say, 0.8% carbon steel, which is Eutectoid steel. So for Eutectoid steel, temperature versus time diagram would be something like this, and this temperature, this is martensitic start temperature, this is martensitic finish temperature. Above this nose we have pearlite cores, you have pearlite near this nose line, fine pearlite. Here you have bainite, we call it upper, commonly known as upper bainite, lower bainite. It is close to this region. Here you have martensite plus gamma. Above this temperature everything is austenite, gamma is austenite. This temperature is known as A1 temperature, or say eutectoid temperature, TE. Here you have everything martensite, and in this region you have gamma metastable MS. Gamma MS is metastable martensite. So in this region you have gamma plus pearlite, here you have gamma plus bainite. So austenite, cool it down, austenite starts transforming, and then after this line everything is bainite. Here you have bainite austenite, here you have pearlite austenite. After this line everything is pearlite or bainite. Before this line everything is metastable austenite. This axis is on the log scale. For eutectoid steel, this temperature is around, so this is eutectoid, so A1 temperature. This is around 723 or 727 degrees centigrade. Different books you will find it, find different values. So martensitic finish temperature is just below 100 degrees centigrade, and here it will be just above 200 degree centigrade. Say 200, 20 or 15 something like this, and this nose is around it is around 550 approximately, not exactly same, this temperature, and this time here it is about 1 second and then finishing time is about say 10, then you have 10 square, it is log scale, 10 cube, this line will go like this, 10 to the power 4, something like this. So P is Pearlite, B is Bainite. Pearlite and Bainite, only the difference is morphology. So that we will be discussing right now. If we want to understand the morphologies of the different phases, then we need to refer to the phase diagram. So let me just draw the phase diagram, some part of the phase diagram. So this is like temperature in degree centigrade versus weight percentage of carbon. So this is this is only a part of the phase diagram. So now this is a part of the phase diagram, and this is the austenitic region. So this is austenite. Here you have alpha ferrite, alpha plus austenite. Here you have this part is continuous, it is not shown. In the end you have Fe3C. Here it is pure iron. So it is 6.67% of carbon, having this percentage of carbon, and here the eutectoid still has 0.8%. This composition is 0.02%. So now the temperature, this is 910, this temperature is around 723, and after 600 degree or something like 550, the solubility goes down and it becomes almost pure iron. So what it tells you, see, we will not explain the full phase diagram here, but this is the part of the phase diagram where everything is solid. If you see, this is pure iron. So alpha iron is having a BCC structure. Alpha iron is having a BCC, body centered cubic. Now here above this temperature, in this region everything is austenite. Austenite is having an FCC, face centered cubic structure. Now you see the austenite, the maximum this point can have 2.2% of or 2.1% of carbon. So the maximum solubility of carbon in austenite is 2.1% at around 11, 25 or 40, in between this temperature range. After that it goes up. You have the other region. So now when you have a steel having this percentage of carbon, it is called eutectoid steel. On this side it is hypo-eutectoid steel. On this side it is hyper-eutectoid steel, and on this line it is eutectoid steel. So here we are going to first explain the morphology, how the phase evolves during solidification. Suppose you have a eutectoid steel. So we know on this axis this is percentage carbon. So what will happen when you cool? Suppose you have the material at this temperature. Now when you cool, what happens? The austenite will be, you have, say you have everything austenite there, all are gamma. It is having a composition of 0.8% carbon. The moment you come at this eutectoid temperature 723, whatever the temperature is, the eutectoid temperature, say here it is 723 degree Celsius. So at this temperature what will happen, the gamma will be unstable and eutectoid transformation will take place. Gamma will be decomposed into alpha plus Fe3C at 723 degree Celsius. This is during cooling. So gamma has 0.8% of carbon. Now it will become alpha with 0.02% of carbon, and Fe3C will have 6.67% of carbon. So this is the carbon percentage, this slide. So the question is how this, this formation of this and these phases takes place. So or the pearlite, this together is called pearlite. Of course you get this pearlitic transformation when your cooling rate is relatively small, actually, as you can see here. So how this the phase evolves. Gamma, so everything is gamma. So what happens now when you reach to this temperature, at the grain boundaries some cementite will be precipitated and then it will grow. Similarly, when the cementite is nucleated and it grows like this, you get, there will be a large number of parallel plate of cementite. So these are Fe3C. So cementite nucleates at the grain boundaries, then they grow inside the grain like this, but they also grow laterally, they also become thicker. So cementite will grow, but the space inside is called alpha ferrite. So you have cementite, you have alpha ferrite, you have alpha ferrite, you have cementite. So this cementite is the black region. So this is the grain boundary. So you have austenite, here you have alpha, here you have, this is Fe3C. So the carbon percentage varies. So this is what the structure actually looks like. So these are alternate layers of cementite and ferrite, cementite and ferrite, cementite and ferrite. So it happens in all the grains, and it can have different directions. So sometimes it can be continuous through grains also, through grain boundaries also. It can cementite can precipitate here or nucleate, and then it can grow in both the crystals. Why the cementite will nucleate in the grain boundaries? Because grain boundaries are the higher energy site, and the higher energy site means there are some distortions in the lattice structure. So there the cementite can easily nucleate. Then once it is nucleated, then it will grow in in a direction which is generally normal to the grain boundaries. So it will grow like this, you will have like this, and ultimately all the austenite will be gone and you will end up getting only cementite and ferrite. So they will not intersect with one another. So these are called different colonies of pearlite. pearlite colonies. So these are called lamella, different lamellar structure. Lamellar structure of alpha and Fe3C. So pearlite has a lamellar morphology. So pearlite is lamellar structure of alpha ferrite and Fe3C cementite. So alpha has BCC structure, this has orthorhombic. Orthorhombic. So now the question is, let us see in detail how this nucleation actually happens. These are called pearlite colonies. So this growth will be stopped when they impinge with another colonies. So pearlite will grow, nucleate and grow, cementite will grow, and you end up getting pearlite, but the growth will be stopped when they encounter the another pearlite. So the colonies, different colonies will have different orientation. Now this distance between these two alternating the distance between this ferrite and this ferrite, two consecutive alpha or two consecutive cementite layer is called interlamellar spacing, lambda. Lambda is interlamellar spacing. And this interlamellar spacing, if it is, when you say your pearlite is coarse, means this spacing is more. When you say your pearlite is fine, that means this spacing is fine. So whether you have a fine pearlite or coarse pearlite, that will depend on undercooling, and depending on undercooling their thickness varies. As a result, you end up getting coarse and fine pearlites. So the property also, the strength also varies, or say other chemical properties also varies. So because when you have coarse pearlite, you have less boundary, so definitely the strength will be varied. So now let us see in detail actually how this nucleation occurs. Let me erase this. Suppose you have austenite, gamma, gamma, gamma. So now austenite is having 0.8% of carbon. At this temperature it is stable, but if you come down it will not be stable. So it will try to remove the excess carbon. While removing the excess carbon, what will happen? Some carbon will try to precipitate out at the grain boundary, say one here, one here, one here, at different locations it can precipitate. Suppose here also, suppose we consider one Fe3C particle is nucleated here. Now once it is nucleated, now Fe3C, what will happen? Generally they try to grow in some particular direction, inward the inside the crystal. Now once suppose you have a, say this is one Fe3C, this is the grain boundary, this is the cementite particle nucleated. Now although we have studied all along the nucleation of spherical nuclei, but spherical nuclei is rarely, almost never seen actually in practice or in any material, because materials are crystalline in nature. You never see spherical nuclei. So it will always have certain shape. Suppose this is one Fe3C nucleated. So in order to nucleate one Fe3C, Fe3C is having a higher carbon percentage. So it has to take carbon percentage from the surrounding material. So suppose let us draw it in different ways. Suppose this is one Fe3C. This is the grain. Say this is one Fe3C particle or plate, is nucleated. Now for this plate to nucleate, what will happen? Initially everything was austenite. It was having a carbon percentage say 0.8%. Now to nucleate, it has to increase the carbon percentage. So what will happen? This was part of the grain boundary. The surrounding material, the austenite, has to release some carbon, reduce the carbon percentage. So near the Fe3C, the carbon percentage in the austenite will be dropped and it will reach the overall composition. It will drop. So it will be on the both side. So what will happen? Now suppose the region of the material where the carbon percentage is say less than this 0.02 undercool, this critical or the this threshold value. So if the surrounding austenite has now, because it has given the carbon atom to the ferrite, from here also it has given the carbon atom to the cementite, it has given the carbon atom to the cementite, also the material from surrounding has given the carbon atom to this cementite. Now their carbon percentage will be less than 0.8. If it is less than say 0.02, this region in the material will become alpha. Now once they become alpha, then what will happen? It will try to grow like this. So when it will try to grow like this and this, how will it grow? In order to grow, now you have this, so this is Fe3C, this is ferrite. So now if it wants to grow, this Fe3C will also try to grow in this direction. Now in order to grow in this direction, it will take more carbon atom from this surrounding ferrite, and this ferrite, in order to grow, it will release carbon atom to this direction as well as this direction. It will also release to this direction as well as this direction. Now what will happen? Now it will become bigger, it will also become bigger, but here the material just next to it will become rich in, here the carbon percentage will again increase. So it will become again Fe3C, it will become alpha, here you will get another Fe3C phase, here you will get alpha, here you will get Fe3C. So that is how you get alternate layers of alpha and Fe3C, because when again I am repeating, once Fe3C is formed, how it is formed? It will take some carbon atom from the surrounding. So the surrounding, the carbon atom will, the concentration will drop, and where the concentration is less than 0.02%, this region will become alpha. Here also, on this side also, it will become alpha. Now all of this will try to grow in this direction laterally. So alpha to grow, the austenite has, here it is austenite, it has got 0.8% carbon. So it has to release the austenite. So austenite, it has to release the carbon. So austenite will try to release the carbon so that alpha can grow. So which is shown here. So to grow, now around this you will have higher carbon concentration. Now once you have one cementite, another one ferrite, another one ferrite. So what will happen? Now ferrite has grown, but how? By depositing the carbon atom at the interface. So here you will have again high carbon, very high rich carbon region. It will become, if this concentration here, it will be more, it will go like this, drop like this. So if the concentration is less than greater than, so in this region where it is greater than 6.67%, it will become again cementite. Similarly here also the same thing happens. So if it is more than 6.67%, it becomes cementite. So this is how they grow sidewise, but this is one. So you have suppose now you have got one Fe3C, and then you got again ferrite alpha. So here you have 6.67%, here you have 0.02%, but this is the grain boundary. But here suppose you have gamma austenite. Now they will, this once cementite is nucleated, it will grow not only in this direction, it will grow inside the grain also, in this direction also. So this growth we have just explained how they become thicker. Now how they become bigger in diameter, if it is a plate, how they become bigger in diameter, this is what we need to explain. Suppose you see you have now everything, the system is in equilibrium, whatever the temperature is, there is some driving force for this to grow, because this is not stable at this temperature. So it will try to convert into these two phases like this. But how will it be happening? So if you see, suppose if you draw the free free energy versus composition, say carbon percentage. So suppose austenite has, for example, this is gamma, say this is the 0.8% carbon austenite. This is G is free energy. We have already discussed what is free energy and all, so we are not discussing again. Suppose now the alpha, say this is the alpha is stable, cementite is stable, austenite is not stable. So the free energy curve will be below this austenite. So suppose these are the two free energy curves. Here the composition is 6.67%, and here the composition is 0.02%. So this is alpha and this is Fe3C. So what happens, because this alpha free energy is high, you see, now they form a composition of alpha plus Fe3C, thereby it reduces this much of free energy. So this is the driving force delta G B that we know. This is the driving force. This is how the free energy is reduced, by forming gamma to alpha plus Fe3C. Now suppose if you see this here gamma is in equilibrium with alpha, but here gamma is in equilibrium with Fe3C. So equilibrium means common tangent. So if you draw a common tangent from this and this you will get a line something like this. So the composition is, this is the say composition, say we call composition of alpha, then Fe3, sorry, so this is the composition of alpha and gamma, equilibrium between alpha and gamma. And now this here is this interface Fe3C and austenite is in equilibrium. So if you draw another line, common tangent between Fe3 austenite and Fe3C, this is the equilibrium composition. So this composition is say gamma and Fe3C, gamma versus Fe3C. Now you see what it tells you, that if alpha is in equilibrium with austenite, the concentration of carbon will be high. So here the carbon percentage is actually more compared to the gamma and Fe3C interface. Here it will be less. So here it has the carbon percentage which is say C alpha gamma. Here you have at the just at the interface you have C gamma Fe3C. So that means what? You have a concentration gradient from this to this. Alpha has 0.02% carbon, 0.02% carbon, but ahead of alpha you have so much of carbon, more than 0.8, but here it requires 6.67% of carbon, but the carbon concentration is less. That means the carbon here will try to, the carbon atom, these are there, they will try to jump like this from this side as well as from this side. The concentration gradient will depend on this thickness or say half thickness, lambda by 2 interlamellar spacing, lambda by 2. So you have delta C is C alpha gamma minus C gamma Fe3C. This is the concentration and the distance is dc dx, this by lambda by 2. So this concentration gradient, so flux will be minus d, say delta C delta lambda d by 2. So delta x we can say this is will be lambda d by 2. So this flux actually, that's why carbon atom will jump from here to here. So as a result what will happen, this alpha as well as if carbon percentage drops, the alpha will grow, and if carbon percentage here increases, this Fe3C will also grow. So this is how the growth takes place in this direction. So I hope you have understood this, how this this parallel plate of alpha this Fe3C happens in both the direction, this direction as well as sidewise. Now when they encounter, say if similar thing happens from say another grain boundary, this growth is happening in this direction, so when they encounter with one another, this growth will be stopped. So these are called colonies. So if you have higher undercooling, then diffusion can occur, but diffusion will be decreasing with time. So this becomes thinner in size, and also the length will be not so so long and continuous. There sometime it will be broken. So what happens? This is how this is how the growth happens. So finally what you get, all the austenite will be converted into different layers of pearlite. So although these are shown like continuous, it will not be continuous. You can say here you can have in this direction also. So this is called pearlite, lamellar structure. So this is the mechanism of pearlite formation. Now fine pearlite means the interlamellar spacing will be less, small. Interlamellar spacing will be small, very small compared to coarse pearlite. Sometime you may get broken also. This line might get broken somewhere, but it is not so. This spacing will be less. So this is what coarse pearlite and fine pearlite. Because if your undercooling is high, temperature is less, so you have more driving force, but diffusion will decrease. So you have more number of nucleation sites, but the growth is progressively becoming difficult. So it will not grow much. I mean, it will not be thick actually in this case. So you become, and the spacing becomes very less. So these blacks are Fe3C and the space weight is alpha.